Ladies and gentlemen, thank you very much for coming along here today. My name is Leniza Enikeeva. I am from Novosibirsk State University and Ufa State Petroleum Technological University, Russia. I'm looking forward to talking with you today about gravitational search algorithm for estimating the kinetic parameters of the propane prereforming reaction. Optimization problems can be found in almost all engineering fields. Thus, the development of optimization techniques is very essential for engineering applications. Most of the conventional optimization techniques require the gradient information, and hence they cannot be used to solve non-differentiable functions. Moreover, such techniques usually suffer from getting trapped in a local optimum in solving complex optimization problems with many local optima. This means that researchers now have to develop a better optimization methods to solve real-world engineering optimization problems. Recently, many heuristic algorithms have successfully been applied for solving intractable problems. Randomization provides a good way to move away from the local search to the search on the global scale. A growing interest has been observed in metaheuristic methods over the last 2 decades. Figure 1 gives the search result of the number of related studies for the metaheuristics on Google Scholar website. The algorithms are genetic algorithm, particle swarm optimization, etc. As you can see, GA and PSO have the largest number of papers. At present, metaheuristic methods have been used successfully to solve a lot of engineering optimization problems. In this work, we will consider the application of a metaheuristic algorithm, namely the gravitational search algorithm, to solve the inverse problem of chemical kinetics. In recent years, some metaheuristic algorithms, such as particle swarm optimization, genetic algorithms, have been applied to solve chemical kinetic problems. However, there is still no persistent conclusion to select a certain algorithm to solve inverse problems of chemical kinetics. This work is devoted to the implementation of a gravitational search algorithm, for short GSA, for finding the kinetic parameters of an important industrial chemical process. GSA is one of the powerful metaheuristic algorithms currently available. Despite this fact that GSA appeared recently, it's already widely used. Let's now take a look at the mathematical model of chemical reaction. The process under study is propane prereforming into methane-rich gas over nickel catalyst, which is an industrially important chemical process. The reaction scheme consists of 2 reactions: propane steam conversion and CO2 methanation. The reaction rates are expressed according to the Langmuir-Hinshelwood model. The ref and met indexes refer to prereforming and methanation reaction respectively. The mathematical model is a system of equations of material balance. The mathematical model of chemical kinetics problems is a system of differential equations that describes the variation in substance concentrations over time or catalytic layer according to the rates of reactions. The system of differential equations is a Cauchy problem containing the initial data. The numerical solving of such a system of equations is a direct problem of chemical kinetics. And determine the kinetic parameters of reaction stages by comparing calculated values of substance concentrations and experimental results is an inverse problem of chemical kinetics. The mathematical problem is to minimize the functional f. From here comes the optimization problem. Let's move on to a brief description of the gravitational search algorithm. Rashidi proposed GSA in 2009. In this metaheuristic, search agents are objects, and their success is proportional to their masses. The objects pull one another by the force of gravity. This force causes the movement of light agents toward heavier mass agents. The communication of agents is provided through gravitational force. The exploitation for the GSA is guaranteed by heavier masses that move slowly. Each object has a position, an inertial mass, a passive mass, and an active gravitational mass. Each object represents a solution that is directed by setting the gravitational and inertia masses. The heaviest agent is the current best solution, and other agents are attracted by this agent. GSA applies the Newtonian laws of gravitation and motion. Each object attracts every other one, and the gravitational force between two objects is proportional to the product of their masses and inversely proportional to the distance between them, r. In order to be computationally effective, GSA uses the value r instead of r squared. The law of motion is that the current velocity is equal to the total sum of the fraction of its previous velocity and the change in the velocity. So now we have discussed the algorithm, and now we can proceed to testing this algorithm. To evaluate the proposed GSA, benchmark functions were used. These functions are classical functions which are often employed to check the optimization performance of different algorithms. All test functions have been listed in Table 2, where D indicates dimension of the function, range is the boundary of the function's search space, and optimal is the global minimum. Furthermore, f1 to f3 are unimodal functions, whereas f4 and f5 are multimodal functions. To compare the optimization performance among different algorithms, we use the next quality indicators. Mean value and standard deviation are good indicators to measure the obtained solution quality. The smaller the mean value is, the stronger the global optimization ability of the algorithm is. The smaller the standard deviation is, the more stability the algorithm is. Table 3 shows the statistical results. Moreover, the best results are highlighted in bold. We compared the performance between GSA and 5 state-of-the-art algorithms: Kaku Search, Gray Wolf Optimizer, Whale Optimization Algorithm, Particle Swarm Optimization, and Sub-Swarm Algorithm. The gravitational search algorithm shows not the best, but quite acceptable results. The conversion curves of the best objective function value for benchmark functions f1 to f5 is shown in figure. This chart provides that GSA can attain the best parameters in less than 250 iterations. After testing the algorithm on benchmark functions, the GSA was applied to solve a real problem, namely the inverse problem of chemical kinetics. As a result of solving the inverse problem, the values EREV, EMAT, KREV, KMAT, B, and N that included in the expression of reaction rates were optimized. When solving the inverse problem, the values of energies and K's varied, while the value of B varied from 0 to 5 and M from 0 to 2. The obtained optimal values were used to solve the direct problem on chemical kinetics, and the values obtained as a result in inverse problem. You can see in the table 4. Figure 2 shows the results of calculations for experiments on propane pre-reforming. The model correctly describes the available experimental data, as you can see from this chart. Points are experimental data and lines are simulation. And the sensitivities of two important parameters such as population size and G0 were studied. In the case of population size, 11 different values of population size in GSA, that is 500, 600, etc., were considered in this analysis. The outcomes of functional F are reported on the chart above. According to the value of functional F, GSA with population size from 500 to 1100 performs better than GSA with population size from 1300 to 1500. However, GS with population size from 500 to 1100 requires more than 7 iterations, whereas GS with population size equal to 1400 requires only 5 iterations. But the value of F is high. From this analysis, it can be concluded that the performance of GSA is highly sensitive to value of population size. And population size from 500 to 1000 is recommended in this work. For G0, 12 different values are considered to analyze the sensitivity of G0 in the performance of GSA. It can be seen that from the chart below that the performance of GSA is better with G0 equal to 150, 180, and 240, where the value of functional F is less than 0.025 and it requires less than 6 iterations. However, the nature of the dependence of F on G0 is not linear, so it can be concluded that the performance of GSA is not highly sensitive to value of G0. This analysis suggests that G0 equal to from 150 to 240 in this work. Let me briefly summarize the main issues. In this work, the algorithm of gravitational search was developed. The algorithm has been tested on 5 benchmark functions, and the algorithm has shown good performance. After that, the inverse problem of chemical kinetics was solved using the developed GSA. The optimal values on the kinetic parameters of the reaction were found. It was proved that the model correctly describes the available experimental data. The sensitivity of two important parameters such as population size and G0 were studied. Ladies and gentlemen, thank you for your listening.